Swayam Prabha. Digital India. Educated India.
Namaste and welcome to the course on Advanced Computer Networks. I am Samir Kulkarni. I'm a faculty in the discipline of Computer Science and Engineering, IIT Gandhinagar. The picture on the right side of the slide is our universe in this course. What I mean by this is that all the content that we are going to cover stems from what we are looking at this picture. And you might have guessed by now that this picture is exactly the snapshot of the internet. And the snapshot was taken long back, around 2008. However, it already looks so complex, right? And the colors here in this picture represent the different internet domains, and the vertices represent the servers that serve the internet content to you. And this is exactly what we will learn and understand what it means to make such an internet architecture and what were the challenges thereon and how the networking or the research community has tried to address these concerns. So the roadmap of our learnings looks somewhat like this. So that we begin with the traditional networks and try to understand what the networking community or the researchers termed as internet impasse and network ossification. Thereafter, we will try to look into the approaches that were taken to deossify and disentangle the internet impasse through the concept of softwareization. And then we will learn about the key aspects of softwareization, including network virtualization, software-defined networks, network function virtualization, and potentially end-to-end network slicing in the case of 5G. And then we will switch the gears and try to understand the next aspect, that's data center networking. And data centers are in fact the core infrastructure or the real enablers of the cloud computing or the edge networks that are going to come in the era of 5G and 6G. But before we begin our today's topic, let me quickly introduce you to the course of material that would come handy for you. And the textbook that I have shown here, the Software-Defined Networks Systems Approach by Larry Peterson and Bruce Davey, would be the most relevant book for the following lectures in SDN. Note, however, that we will not be covering this textbook in its entirety. Only certain bits and pieces relevant for the scope of software-defined networking would be addressed. Also, if you are a systems design or architecture enthusiast, I would recommend this book, Network Architecture, Return to Fundamentals by John Day, as you will find it interesting and insightful to understand the networks and the evolution from the architectural point of view and where things have gone wrong and where things have been right. But this will not be the scope for our course. And I also expect that you would have already gone through one of these basic undergraduate level networking textbooks, like Computer Networking by Kouros and Ross or Computer Networks by Andrew Tannenbaum. And I assume most of the concepts on the networking that these textbooks offer would have been covered by you in your earlier undergrad course. If you're interested in learning about how to develop network stacks or build the TCP/IP stack the way it is in the Unix or the Linux systems, the book on Richard Stevens would be very useful. I have also listed here some of the important online materials that may be of use to you at later stages of this course, especially the Mininet or the network emulator for the SDN, where we are going to cover certain topics and do some hands-on, provided we have enough time, and also have you do some work as assignments on this. And as we go along, we will also be covering several of the important research publications from both academia and industry that have influenced and shaped the computer networks. And in my personal opinion, I consider learning computer networks would be incomplete without the readings of the Internet Engineering Task Force's request for comments or the internet and the internet drafts. So I have also planned to cover and point certain relevant internet drafts as we go along. And lastly, and most importantly, I would also like to acknowledge that the lecture materials that I'm going to present here in the course of next 5 weeks is built from the lecture materials from the following sources. Okay, to quickly summarize what our learning journey looks like I said, it's essential to begin with the traditional networking, and not in terms of the concepts of what the network is built, but the key principles and the design philosophy behind building such a network stack, and what it means as an end-to-end argument in networking. And then look into the key issues that align due to the evolution of the network, following or not following specific principles, and understand these terms of internet impasse and ossification. Next, we will look into the modern day networking that we plan in the view of the softwareized networks, considering network virtualization, software-defined networking, network function virtualization, and the associated use cases. And then in the last phase of this course, we will look into the softwareized, not just the softwareized, but also the programmable networks, namely the P4 or Programming Protocol Independent Packet Processors. Thereafter, we will look into the real enablers of cloud, that's the data centers, from the networking perspective. And I take it for granted that we are all familiar by now with this 7-layer ISO OSI model that's shown on the left side of this slide, and also the 5-layer TCP/IP model shown to the right of this slide. But then we might have learned what the physical layer, data link layer, network layer, transport layer, and application layer do, and the associated protocols to a great extent. But the key questions that I want to pose are the following. One, why is the stack built the way we see it now, right, in terms of either the TCP/IP model or the ISO OSI layer model? Especially on what principles, if any, was it built? And then, more importantly, we would also want to question and understand, could it have been done any differently? Right? And to answer these questions, we would have to step back a bit and peek into the history and understand the evolution of the computer networks. So let's try to do that in the view of the evolution as well as the key works that have influenced the evolution. And the first, in terms of the principles of networking and the design philosophy, I present to you the 3 papers here. The first is this paper from Winton Cerf and Robert E. Kahn, who are considered the founding fathers of Internet. And this work, in fact, put forth the philosophy of Internet working and laid down the mechanisms for handling the aspects of addressing, routing, and the means to support multiple reliable connections over an unreliable connection on an unreliable network, the variations in the packet size, accommodation of fragmentation, and flow control aspects. And in fact, this is the first work that brought the notion of Internet protocol, or in a clear sense, one protocol as the center of the hourglass. And we will speak about this in greater detail as we go forward. And then the 2 other papers, the end-to-end arguments in system design, which is the most cited work, as you can see, roughly it has garnered around more than 3,500 citations. And the reason being that is the core principle that theorized what it means to provide the functionalities for the network. We will look into this in details as we go. And the other core work by David Clark, in terms of the design philosophy of the DARPA Internet protocols, more a reflection as well as what are the supposed suggestions of how the Internet protocols have to be. And this work fundamentally put forward the lot of objectives for the Internet protocols. And this objectives as primary and secondary values, and were put forth to say what should be the key role of Internet. And it stemmed from this work that the primary goal for an Internet is always the reliability and survivability of the communications. And it needs to support multiple heterogeneous networks to operate and work together. And these were preferred over the cost efficiency and accountability. And as a result of these, what we now have an Internet is not a centralized entity, but a decentralized and distributed collection of networks. And across all these works, what we also see in common is in the design of the Internet Internet, the most important emphasis has been on the simplicity preferred over the complexity. And as a result, instead of having the mechanisms in IP to make sure that packets are delivered correctly, we see the burden being pushed to the end hosts, and IP or the network layer being as simple in just being the best effort service. And all of these design criteria together have led to this highly decentralized internet architecture, which, by the way, is somewhat reliable but not as much accountable. And another important aspect also comes along in the design of internet is the fate sharing concept that was put forth in the design philosophy of DARPA internet protocols, where the concept is all about saying that either you fail in all or work together, right? So that whenever there is a failure, everyone fails. And this is exactly an example of how the end-to-end principle operates. And also the concept of saying that the information or the state better be stored on the end hosts rather than at the transport layer or in the network. So let's look at this evolution in greater detail. The internet, or rather the quest for networking, started way back in 1960s. And this was a way for government researchers to share information. And if we look back at the 1960s, the computers then were very large and almost immobile. And when I say large, they used to be like the mainframe computers that would occupy more of a big size as this room of a large size. And that made them definitely immobile to move the information. And the only way that the information could be moved or obtained from a particular machine would be that either you travel to the site and get access to that mainframe computers, or have the magnetic tapes through which you can back up the content and send it over the post. And these very reasons made people to think of alternatives to share the information. And the US Defense Department, which was pioneer in looking at these alternatives, eventually led to the formation of the ARPANET, or the Advanced Research Projects Agency Network. And the whole aim then was the sharing of the information that can be done through the network. And during these times, in the professors at various places were also looking for building these networks. Donald Davis at the National Physics Laboratory in UK, Paul Baran at Rand Corporation USA, and Leonard Kleinrock, who was then the MIT PhD student, were looking forward for the packet-switched networks. And the work by Lord Kleinrock showed the effectiveness of the packet switching network. And this fundamentally laid down the aspects of what we define today's internet, which is a packet-switched network. And those evolutions of the packet-switched network stem back to the early days of 1960s when the ARPANET started to operate. And the first ARPANET operational node was achieved in December of 1969. And what we achieved was exactly this 4-node network that you are seeing on this slide here. The first of the node was at Stanford Research Institute. And this node was basically a mainframe SDS 940, which was a 24-bit mainframe system. And the second node was at UCLA, made of the SDS Sigma 7 mainframe system, which was a 32-bit mainframe device. And the third node was located at UC Santa Barbara, and which ran the IBM Systems 360/75 mainframe. And this was a 32-bit machine. And the fourth node was the University of Utah, which ran the PDP-10 mainframe device. And interestingly, this machine was a 36-bit machine. So you can see the heterogeneity where one 24-bit machine at Stanford Research Institute, a 36-bit machine at the University of Utah, and two 32-bit machines at UCLA and UCSB were all connected to make a first 4-node network. And the backbone connections were made using the 50 kilobits per second links laid down by AT&T, which is nowhere near to what we look at the today's network of more than 1 gigabits to several gigabits per second links. Interestingly, you would also see a processor called the interface message processor, which was exactly what we call today as the network gateways or the routers. And you can see this fridge-like device here sitting there to facilitate that communication. So this was added on to these mainframes to facilitate this network communication. So now imagine this versus a router that you can hold in your hand, right? So that's the evolution that we are speaking about. And nonetheless, all of it started with these kind of devices. And then the first protocol for facilitating this communication, called the Network Control Program, or backported to say Network Control Protocol, happened to exist to make these networks devices to talk. And as one would say, the first connection that was tried on this was between SRI and UCLA. And as we would have, it crashed the moment the third character was transmitted. And apparently the login was the first word that was tried to be transmitted. And as soon as it got the third character G, the device at SRI crashed and they had to restart the machine and to get it working. But nonetheless, it succeeded. And then that led to the first operational networks. And thereafter, this network evolved, and over the years, by 1972, the ARPANET reached around 50 nodes spanning several of the universities in US. And then the evolution continued. And in the era of 1970s to 1980, several of the internet or the networking principles came out. And the main is this Cerf and Kahn work that laid down the key internet working principles, which can be summed up as saying the internet working should be based on minimalistic approach with no autonomy whatsoever. And by the sense of autonomy, we mean the changes that are required to interconnect networks should not be owned by one entity. And what this also meant is to facilitate and support the evolution of heterogeneous networks. And the whole role of the network needs to be the best effort service model, in that once it takes the data, it tries to do its best to deliver the data to the other end and not have any state embedded in the networks, that is essentially the stateless routers, and decentralized control. And these are the key founding principles that define the today's internet architecture. And also by 1976, Ethernet had as a what we know as IEEE 802.3 came out and led the way for the Ethernet-based connections. And there are also several proprietary architectures of network that were proposed, including TechNet, SNA, and XNA. Later, several of the networks started to grow, and by 1979, we would have ARPANET grow around 200 nodes. That's from 4 to 200 nodes in around 10 years. Thereafter, the evolution continued, and many things came to shape. And the most critical thing that really shaped the today's internet is the arrival of the TCP/IP protocol stack in 1983. In fact, the foundations of TCP/IP protocol stack were laid long time back by the Winton, Cerf, and Kahn's paper, but the actual deployment happened on January 1st of 1983, which is also known as the Flag Day. Working went on to change to use the TCP/IP protocol and replace the earlier NCP protocol. And this is the only time in the history where we have had a change that has occurred on just one day. And this is also the last of such thing that to happen, because the internet grew and it no more is feasible to change anything in one day. And the deployment of TCP/IP, in fact, led to the emergence of lots of new protocols. And then again in 1983, the role of a DNS in terms of how you would want to identify the IP and associate IP with a name, or what is called the address translation, came into picture. And then around 1985, the FTP protocol was rather redefined. In fact, FTP has a very interesting history. Prior, Sri Abhay Bhushan, an alumni of IIT Kanpur, introduced the FTP in April 1971, while he was pursuing his master's at MIT. And thereafter, it was reshaped to suit the TCP/IP model, and the new FTP was defined in 1985. And then the networks started to emerge, including the national networks like CSNet, BitNet, NFSNet, Minitel, and so on. And what really started to happen was the widespread usage with more than 100,000 hosts connected to this confederation of networks. And in fact, when we scale a lot, we also started to see several anomalies in the operations of the network and what was termed as the congestion collapse. That was the time when the internet hosts would send their packets, but the end hosts on the receiving end would never receive those packets due to the packet drops that used to happen at these intermediary router devices. And the hosts that were trying to send the packets would wait, and as they see no acknowledgement coming back, they would retransmit the packets, leading to even more worse congestion. And that's when, during 1988, the work by Van Jacobson tried to address this congestion and provided the mechanisms for TCP to control the congestion and work through the congestion aspects and provide reliable communication. And all these aspects led to a widespread usage of the internet, and several of the internet applications started to emerge. And most notably, the one that has shaped the current internet to the most is this emergence of the web. Web, or the World Wide Web, WWW, is nothing but a system of interlinked hypertext documents that are accessed via internet. Right? And the web was originally conceived and developed to meet the demand for automated information sharing between the scientists in universities and institutes around the world. And this was the proposal that was put forth by Tim Berners-Lee and his colleague Robert Caliu in 1989 at CERN. And in this way, once this web gained popularity, there were no limits, and lots of new aspects started to shape the internet. And in 1994, we had the first Mosaic or the Netscape web browser, and thereafter, the commercialization phase of the web or the internet started to take shape. And with this, several technological advancements fostered the widespread adoption of the internet. And just to give this aspect, like the deployment of the broadband access started to take shape, and the high-speed wireless access also started to come into picture, and all the high-speed gigabit Ethernets were also becoming more and more prominent. And once it became accessible to most of the users, even the applications like Facebook, which was a social network at that time, which started with roughly around 1 million users in 2004, and now, as of, if we estimate, the scale spans to around roughly 3 billion active users on day to day. And this shows the emergence of the internet and its widespread scale that it has gone. And in fact, several of the service providers like Google, Microsoft started to create their own networks and provide several of these specific services like search, email, and the Google Classrooms that we would have used during the COVID times, and you name them. There are many more services. Now we cannot think of a service without internet, right? And including the services that universities, the e-commerce sites all try to adopt the cloud as a notion which is not accessible without the sources of the network. And as I speak today, we have a world population of roughly 8 billion, but the internet population, and by internet population, I mean the users, the devices that are connected to the network, including the infrastructure of the internet, including the switches, the routers, and the middle boxes. The population of the internet is roughly 30 billion, so 3 to 4 times more than the world population. Right? So definitely this internet growth, which has spanned over more than 60 plus years, has had its positives and negatives. And if you are interested in trying to learn more about each of the aspects of the evolution, I would recommend this website, computerhistory.org, where the timeline of the networking, the web, has been presented to the greater detail, starting from the days of the telex network in 1933, to the date of the evolution in the 5G era. And telex in India was known as Star, was the first modern electronic communication and payment system. And this was, however, decommissioned in India a decade ago, around 2013. So to sum up, we have looked at the internet's evolution, and we take it that internet architecture is evolving faster than ever. And we consider this internet architecture, for our simplicity, into three phases. The first, pre-2010, where I call this the network ossification stage, where several of the closed and proprietary developments happened, several of the proliferations of the standards were done, but many became barriers for the entry. And several of the stakeholders started to play prominent roles. And the second phase, what I call as the disaggregation phase, where the network owners tried to take control of the software. And this happened through the emergence and adoption of SDN and NFV. And the future, or the third phase, in terms of what I call the programmable forwarding, where the network owners not only take control of the software, but also control the way the packets would be processed for them, in terms of having the ability to program precisely what the network needs to do for them, rather than relying on the network or third-party software or vendors to define and dictate what the network would do. So to think of, we may consider the future possibilities of networks being completely programmable and network to emerge as a programmable platform, in the sense that every end user would have the control to dictate and program the way the networks would want to be operated for them. And network, thereon, we can think in terms of the software and consider that there will be these network as a software be programmed by many and operated or basically managed by a few to enable their custom requirements.